Hey, what's up guys? So somebody just sent me one of these new Arduino 101 boards, and I really don't know anything about it really. So this is going to be kind of a different video. I thought what I'd do here is just fire up the camera and let's look at the board itself. Let's see what's so different about it compared to, you know, the other Arduino boards here. Let's look at the specs, let's crack open the schematics, walk through those, see how the whole thing works, and then just kind of give you my thoughts and opinions on it, and then maybe we'll run some example sketches later on and see, you know, what the special features of this board are. So anyway, so it's going to be kind of a different, chilled back, laid back kind of video. So anyway, let's go ahead and get started here. So in typical Arduino fashion, we got the really cool packaging here in a nice little cardboard box. Arduino 101. I don't know what that means. What does the 101 mean? I don't know. And also this is Arduino, not the I don't know what the other one is. Genuino or Genuino. I don't know. So anyway, it says it's powered by Intel here on the box. So obviously they abandoned the AVRs from the other Arduinos for this board. And anyway, so let's crack it open, see what's going on in here. Okay, we got the shielded anti-static bag. That's a good thing. Not just a board sitting in the box. And here's the board. Okay, let's see what else we got in the box here. All the usual stuff here. No stickers though. Usually they hook you up with some cool little Arduino Infinity stickers and the I Heart Arduino and all that kind of stuff. But anyway, that's really not what we care about. This is the board. So it's the same form factor as the, let me rip all this crap off, as your typical Arduino Uno. This is actually a Dwayne Milanova. It's pretty close to the Uno. It just doesn't use the AVR for the USB to serial programming. This has the onboard FT232RL, so they switched over to that for the AVR programming when they went to the Uno. Anyway, okay, so it's the same form factor here. We've got the same headers, I see, barrel jack. We've got a reset button, but on the 101 we've got two reset buttons. We got the full-size USB jack, so that's good. The 6-pin header here. Let's see if there's any difference on the back. Doesn't look like it. Okay. One big thing I'm seeing right away, though, is over here we've got a PCB antenna. So that's kind of cool. And I think I saw in the box here that it's got Bluetooth. I don't know if it's a dual function radio. I don't know if it has Wi-Fi. I guess we'll find out. But we know it's got Bluetooth, so that's, oh, and it's got the Bluetooth symbol right there. So it's probably just Bluetooth low energy only. I do not, oh, there's an FCC logo there. I don't see an ID. Oh yeah, there it is. So it's got an FCC ID number, so that's good. And a CE marking there, so that's good. So this is a fully FCC certified radio, I guess. So that's good. You guys know I'm working on my own stuff here, my own little Bluetooth radio module here. It's breadboard friendly and all that kind of stuff, but it is also FCC certified. But usually when you see that, the radio is under a little shielded can like this one. Not so on this one, but anyway, we'll just keep kind of going through here. So right off the bat, I can tell that they are using this, what is that thing there? Okay, that is the Intel Curie processor. Actually, what they call it is the Intel Curie module, and we'll get into that a little later on when we look at the specs. But this is a BGA component, meaning it's a ball grid array. So the pads for it, or the connections from this part to the board, are on the bottom side of the part itself. So I guess we're not going to be taking the processor off like we used to and putting it on our breadboard, you know. So So it's a BGA part, so that's going to be a little trickier for us home gamers to assemble at home and make our own boards with. So anyway, that's kind of a little drawback. Ooh, what is on there? Okay, so yeah, I'm seeing a lot of cool parts, but once we open the schematic, we'll see what all of those are. Okay, so yeah, let's pull up in the specs here. Okay, so this is the landing page on the Arduino site for the 101. And yeah, you see we've got Arduino 101 and the Genuino, or Genuino, I don't know. I'm not going to try to figure out the marketing stuff there. But so anyway, I don't know, I guess they've got their own little battles there to figure out what the naming is, depending on which country you live in. But we've got some gesture, 6-axis accelerometer, gyroscope, gestures. I wonder how it recognizes gestures. Huh. Okay. I guess we'll figure that out. Control projects with your phone over Bluetooth connectivity. Cool. Okay, so it's saying 3.3, 32-bit, 32 megahertz, ARC core. Okay. This is the Intel Curie module. Okay. All right, that's interesting. So it's also running an RTOS on board, and it's actually a 2-core or dual-core device. The Intel Curie. We've got a quark processor and the 32-bit ARC core, both running at 32 megahertz. It seems kind of slow, actually. I would think that you'd run these at least at 100 megahertz, but anyway. Okay, so we've got all of our standard I/O there. That all looks good to me. PWM, 6 analog inputs. It's saying that it's 3.3 here, but they're protected against 5 volt over voltage. So maybe we'll do some bench testing here and verify all of that stuff as well. So you get the tech specs here. 3.3, 5 volt tolerant I/O input, 7 to 12. The limit is 7 to 20. So that's on the barrel jack input. Okay, just wanted to see if we've got a VIN pin. We've got a VIN pin on the board. Okay, analog in, yep. DC current per pin's 20 milliamps. Okay, so these are the big specs here. Look at this. Look at the size of our flash. We've got 196K of flash. Your ATmega 328P here has 32K of flash, so that's a huge jump. The Arduino Mega, though, that uses the ATmega 2560 has 256K of flash, so it's not quite as, that doesn't have quite as much room as that part, but you've got 24K of RAM. The ATmega 328P has 2K of RAM, so that's a nice big jump there. And 32 meg, Bluetooth low energy, 6-axis accelerometer gyro. So I guess the gesture, what is the gesture? It says it has gesture, recognizes gestures. Like if I wave over it, it'll know that I'm waving over it. I don't see any part on this board that could do that. So there's a little shiny part over by the USB port that looks like it might be able to do something like that. I don't know. We'll have to see. Okay, we'll get to all of that. Okay, so then we've got some cool little examples here. Integrated accelerometer and gyro. We got a step counter. So that's perfect for the accelerometer gyro stuff. Is that you can use this as like a pedometer. Obviously, in this form factor, I don't know how you want to do that, but if you took that part off of the board, put it on an itty bitty board, like this or like this, that might make more sense. This is another board I'm working on too, by the way, with the 328. That plugs right into the Bluetooth board. So anyway, that stuff's all coming down the road. Heart rate using Bluetooth low energy. Monitor your heart rate. So I guess you could strap in some heart rate monitoring sensors, like an IR sensor or something like that, and then with your phone app, plug into that and use the Bluetooth profile for heart rate monitoring. I guess that's the idea there. Again, guys, I don't know much about this board, so I'm kind of just winging this video here. Okay, programming, yeah, straight through the USB. So they're telling us that we do not have a USB to serial converter on this board, so that's cool. It goes straight into the part. Okay. Okay, differences, yeah, okay, 3.3, low power Intel micro, and onboard be okay, got it. Okay, so we might receive an update on firmware from time to time. So it's going to be able to get, it's, you know, like with the Arduino stuff, you've got the bootloader running and then you just upload your sketches in via that bootloader. But with this guy, I'm sure it's running its own firmware to handle all of that stuff, and then, you know, you same kind of thing as the bootloader there, and then you load your sketches through the USB. I don't know. We're gonna have to figure that out once we actually upload a sketch and see how that goes. But anyway, what this is telling you, I guess, is that you can update the firmware right through the IDE. Okay, then we got all the power supply stuff. Yeah. Memory. Okay, so you actually I see. So this is telling you how much. So it actually does have quite a bit more than not 196K of flash, but only 196 is for you in your sketch. The 24K out of the 80K. Okay, yeah, for the RAM. Okay, this all looks good to me. So it might be a little different way of using the serial port there. It feels kind of like the way the Arduino Leonardo works, where, you know, it does not have a USB to serial converter either, because this is using the ATmega 32U4 microcontroller. It's got onboard USB, so you program it through that, but you also can use that as a serial port, so you've got a different way to connect into that. So that's why they're showing the serial one there, and we'll get into that too again once we start loading up some sketches. Okay, cool. Well, anyway, yeah, I don't know. I'm not seeing anything in here that's alarming yet. It's kind of cool. You've got the onboard Bluetooth low energy there. The accelerometer and gyro, I believe, are built into the Curie, which is kind of cool, and the radio too, really. So this is just the antenna for the radio, but the radio itself is built into the part. So yeah, that's pretty cool. So you've got some built-in sensors there. Okay, so let's check out the schematic now, which is really the meat of this board. Now this is where we kind of see all the different parts and what's on this board and how it all works. So okay, so here's the schematic. They've got a little block diagram here showing you all the main parts and how they're all hooked up. So that's kind of interesting, but I don't really care about that. Here is the schematic, and we're looking at about 3 sheets there, so not too bad. Not done in Eagle, and definitely not Altium. This looks like it was done in OrCAD. It might even say that somewhere. Do we have the name of the guy who did it? E.M. Kashi and S. Mangent. Okay. So anyway, this is the schematic. So it looks like they broke this out into little blocks here for each function, which is cool. So it's a little bit easier to read. They didn't just smash it all into one sheet. So, and okay, so right here's our USB power input. This is the USB jack, comes in. Got some nice ESD protection on the data lines there. We've got the 5 volts coming in from the USB here. It's sensed by the Curie. Okay, and then we've got USB 5P00 power, which jumps over here. And then this guy here, what is this thing? This must be V in, V out. This is some kind of protected load switch. So, you know, if it ever detects, yeah, you can see I set here. So you set the current with these resistors here, and if it ever detects an overcurrent down on your board, which this is a good idea to have. It'll kill the power output to the board. So, you know, this is the Arduino board is something where you might use that 5 volts and connect this stuff out to the outside world. And if you got a short out there, this guy here will break that open so that it doesn't, that short doesn't propagate on through to your USB port and you can possibly, you know, blow it up or whatever. So that's kind of nice. I think it does a little bit more than that though. So we'll see here in a second. We've got the overcurrent flag. That would have been cool. They could have popped a little LED there. I don't know. Again, this is not a design review. I'm just kind of skimming through this thing. I'm not sure how every part on this board works, but I've seen these parts work where you've got, you know, an LED here. So in case you did have a short, you could, you know, have a little red LED on the board. Okay, so this is cool. We got a little note here, and you could set these resistors, current limit resistor values. So 500 milliamps, 1.51, or you can short for 1.5 amps. So I guess if you wanted to go full blast with this USB port, and you could pull 1.5 amps, there's a little, oh, there it is right there. There's a little solder pad there that you could jumper across, dab a little solder in there, and you can pull 1.5 amps off of your USB port. The interesting thing I just noticed about this board is they didn't put any reference designators on the board. So that kind of stinks. So like if I wanted to find R12 on the board, well, I'd have to pull open the CAD files to see where R12 is. The other thing too, now that I look at it, there's a little shiny part in there, and that's the part I was thinking, what is that? You know, I'm not sure. I still, is that? Let me see this thing. Okay, so I just had to pull open that part, the FPF 2496, and this is over voltage, over current protection, load switch with adjustable current limit control. And I'm trying to figure out what the package is here. Okay, so this makes sense. So that little tiny shiny part on the board, you might not be able to see, is a tiny little black speck there on the board, is this part here. So you can see it's a little BGA. And it almost looks like a little die chip or something, and it doesn't really look like a standard little IC. So it's itty bitty. Okay. So anyway, getting back to the schematic here. Okay, so we figured that out. I love doing this stuff, by the way, just going through these schematics, trying to figure out how they all work without, you know, any previous knowledge. It's fun stuff. The other thing too here, by the way, is we've got this on B here, I noticed. So this is like an enable for the part. So let's go over and see if we can figure out what that is. Okay, so we've got on here, but is it active true or active, or let me see, what do we got here? So yeah, off. So off is when it's high, on is when it's low. So in order for this to turn on, this signal here needs to be low. So who's driving this guy? Here we go. Power input select. So I guess this controls whether or not your power comes from the barrel jack or the USB input. And we've got this guy here, R3119. Let's throw that into Google. Searching for that, well, who knows what kind of part that is. See, Digikey Mouser, Newark, none of them are coming up. Let's throw it into Octopart. Nothing. Let's try taking some of the characters off here. Okay, here we go. Getting closer. We got it 07A. That's good enough. Let's see what this is. Not the exact part. Ew. No data sheet. Yeah, so this is great. You know, I hate when you get a development board, you go through the schematic, you want to replicate what you see here. This is your known good board, you know, and you've tested everything out with it. Now you want to go build your own, and you can't source the parts. So anyway, I guess we're just going to have to figure out how this one works here. So we've got the DC in 5 to 20, which comes in right, which one is that? Right here. That's right off of the barrel jack input right here. And we'll get to this section in a second, but I just want to figure out how this guy works. And then we divide down for this, the VDD. And this must just be a simple supervisor part. So, you know, anytime you've got some input here that's past a certain threshold, you have an output here. So, and we can kind of figure out how this works as well. So you can see we have this trig true D, which feeds this guy, and we know that this needs to be low in order to turn this on. So means that tells me that when this is low here, because that would be coming from the barrel jack, this signal must be low. Okay, so this is an active low reset output kind of thing. So these supervisor chips will drive you know, your reset pin on your micro and pull it low anytime the voltage falls below a certain value. And I think that's what's going on here, so that when this voltage here goes down to a certain point and you have USB power coming in, then that will drive this pin here low, okay, which will turn this on. And we also have a pull down resistor here, just in case, you know, you don't have anything here or whatever else. And I don't know what the input here looks like, but yeah, so that's how that works. So when you don't have your barrel jack input, pulls this line low and enables your USB power. Okay. And we'll kind of go down here. Oh, duh, look at this. Trip set to 5.75 volts. Okay, so that's actually where this is set for. So when you have 5.75 volts here or greater, this line here will go high, and that enables the barrel jack input and disables the USB. So that's kind of cool. Good to have notes in your schematic. Actually, it would be nice to see that over here as well. You know, some kind of description as to, you know, what the logic here is. All right, and that's a 5-pin device, so that's probably this part or that part. And we'll figure that out later. Okay, so getting down to the barrel jack input here. Okay, so we've got the barrel jack right here. We've got a diode, which is nice. So we've got some reverse polarity protection. Okay, DC in jack. I wonder if that's going anywhere else. You know, what are they doing with that? Then we have the DC in 5 to 20 volts here. And that is what feeds this guy up here. And that also is connected to one of the headers here, the VIN. I'm sure that's what that is. Yeah, the VIN here. And we've got some nice filtering here, 0.1 and a 4.7 with a ferrite. So that's good. And then a whole bunch of caps here. This is interesting. We've got a 10K resistor tied to ground here. I wonder if they actually populated that. But this might be there just to put some load on your barrel jack input there. But you know, if you're going to use this in battery applications, you want your quiescent current draw or your standby current to be as low as possible, and this is just wasting current. So anyway, that feeds a DC to DC buck converter. I could tell right away because, you know, we've got the input here, we've got the inductor on the output here. This must be synchronous as well, meaning we've got top and bottom side FETs to control the output there, so no diode hooked up. And then we'll pull the part number on here. This is a TPS part, so whenever I see that, I know right away it's a Texas Instruments part. And yeah, so we have trig true D going to this guy. And let's pull the schematic, or pull the data sheet for this. Okay, so here is our data sheet for the DC to DC. Ooh, nice little 3mm by 3mm QFN. So that's this guy right here on the board. And it's a fixed voltage out. Okay, so no feedback resistors. You see the feedback pin is tied straight to ground. Yeah, this is a nice part. 1 amp output. So that's rock solid there. And here is our example application schematic here. So yeah, fixed output. We've got the 3.3 volt version. If I go here, yeah, the 62152, 62152, 62153. Wait a second. Oh, my bad. We have the 5 volt output version. I thought that they would have generated 3.3 volts off of this. They're generating the 5 volts. Okay, good to know. And going back up here. Look at that. Nice quiescent current draw. 17 microamps. It's pretty low. Yep, synchronous step down DC to DC converter. Okay, so what I want to see when I look at this application here, I see right away that the enable line is pulled high, so that means it is an active high enable, meaning this part turns on when that enable pin is high. So when we go to the schematic here, remember that this enable here was low true. I mean, when it is low, this part's on. So that's perfect. So what they're doing here is they're feeding both parts here with the same output from the supervisor, so that when it's low here, the USB power is active. When it's high here, meaning we've got barrel jack input, it is driving this part here and turns on the DC to DC converter. See, over here we've already got 5 volts, so this generates the 5 volts. And look, they're even tied together. I think they're the same net. Yeah, 5P00 source VDD1. Same thing here. Okay, so yeah, they're feeding the same thing. And I just thinking about something, you know, yeah, we should be okay. But if this was disabled here and this was enabled here, now you've got 5 volts being applied to this point here. I just wonder if this guy likes being backfed with 5 volts. Might need to look into that. Okay, a couple other things they've got going on here. Here's the soft start pin, frequency select, def pin. What the heck is that? Def pin. Okay, normally I guess you tie that to ground. Let's just do a quick search here and see what that is. Def pin, output voltage scaling. Low is nominal, high equals nominal plus 5%. That's interesting. And they are pulling this high, so they're setting it at 2.5 volts. So that's got to be high for that. And we could even see what the thresholds are. Where is the def pin? Okay, high level for that, yeah, 0.65. So yeah, they are driving that high, so that means that they're actually running that switch mode regulator here. Its output is not going to be perfectly at 5. It's going to be 5 plus 5% of that, right? So that's interesting. Okay, then after that we've got the LM1117D. That is a really cheapy linear regulator with really bad quiescent current draw. You can check out my other videos on my other low power series videos where I talk about quiescent current draw of linear regulators, and I think I tested this one. It was really bad. I think it was like somewhere like 5 to 10 milliamps, something like that. But anyway, this is a fixed voltage output here, 3.3 volts. So now we've got our 3.3 volt rail. And just 10 mic there on the output, 4.7 mic on the input. I would have liked to thrown a few 0.1s on the in and out there. Same thing for this guy too. Okay, so yes, continuing on with this schematic, it's definitely going to be a long one here, But down here we've got the power header here, so that's this part on the board, which is how you can source or get power from the board here. So you get your 5 volts, you get your V in, you got the 3.3, the reset line. And speaking of reset, we've got the 2 reset buttons here, pulling the signals low. We've got, it looks like we've got a little bit of debouncing stuff going on in there. 3 LEDs, communication, fault, and power. Okay, so we've got the RX, TX-RX LEDs. And over here, we've got the D13 green LED. So like, what this is the LED that you normally see hooked up to digital pin 13. They've done the same thing here, so this must come over from the Curie. They've done the same thing here, but they put a driver in here, which is a good idea, so that if you're hooking that D13 pin up to other stuff out, your other sensors or whatever else, they're not going to be affected by this D13 LED here. So this is a higher impedance input here. Because that D13 just so happens to be, the clock on the SPI port, and if you got that LED sitting there going nuts on you, and you're pulling that down on, with your pin, it could screw things up. So anyway, it's a good thing to have this little bit of buffering going on in between the pin and the signal. Okay, and this is all of the Curie stuff here on the next sheet. Okay, so the Curie V3. Okay, so we've got U12 broken out into a few blocks here. We've got power and reset, I/O. Here's the antenna for the Bluetooth, and JTAG. JTAG is actually how they program the Curie itself. So this is, I guess, this is like the equivalent of when your Uno boards here, where you've got this 6-pin in-circuit serial programmer header here, except here we've got the JTAG port, and that's all the way over here, this tiny little thing, and that's how you can connect to it, download new firmware to it, and do live debugging with the part. Okay, but anyway, over here we've got power and reset. Okay, so we've got the come on, there we go. So we've got all the JTAG stuff coming in. Okay, reset line, let's see, I'm just gonna kind of skim through this a little bit here. Okay, so here's the Curie V-Bus Sense coming in here. So that's off of that, the USB, and then the USB data lines there. All the V-in stuff. Wait, actually they're connecting all that to ground. V-System here. V-System, let me zoom out here and see that, because I don't see a V-Sys up here. So what are they doing? Here we are. So the 3.3 comes in here, and then through 2 0-ohm resistors, we generate V-Sys and VDD Plat 3.3. Okay, so it is 3.3, but this is so they can segregate those 2 rails out on the board. Okay, so yeah, V-Sys coming in right here. Only have 1 input for V-Sys on this part. It's interesting. Okay, the 4.7 and 0.1 mic hooked up there. We got PV-BAT, which I did not see anywhere on the board, but that's kind of interesting. Looks, in charge status, battery iSet. So this is cool. So this must have a full-blown battery charge controller built in as well, and you could probably do battery voltage monitoring, fuel gauging, all that kind of stuff. But it's not used here on the 101 board. Okay, yeah, that's interesting. What else do we got going on here? ESRV-BAT. Okay, this is cool. So we've got some buck controllers built into the part as well. So this is an interesting part. So it's got a PMIC, so you could generate other rails with it. So it's saying 3 volt buck not used, the 1.8 volt buck not used. They're saying that, but over here you actually are using the 1.8 buck, and then it feeds back. Or maybe they're not using it. I don't know. It's interesting. This rail here doesn't appear to go feed back into anything. EDD plat. Okay. But anyway, that's interesting though. And I do see an inductor right there on the board. So that tells me that that's for this part here. Again, no reference designators, so it's kind of hard to tell. But okay, so up here we've got the VDD plat 3.3 coming up. So this is the separate rail from vsys, and it looks like it's used for all of the I/O stuff up here, and it feeds all kinds of stuff. So it feeds right in the I/O VCC, comes down the comparator 3.3 VCC, the buck vselect, and the VDD BLE sensor. I don't know, but it looks like that's the rail for the BLE radio. And then we've got a little bit of filtering here, which creates a new rail here that goes to the comparator AREF and the ADC 3.3 VCC. So that's, filtering out the nasty 3.3 that's going to all the I/O stuff for your analog pins there. So, okay, so then we've got all of our analog inputs here. We've got the BLE antenna here going out. Okay. And then all of our pins cooked up here. A lot of no connects in there. Coming right in. Okay, cool. Over here we get all the test points. Yep, and that's pretty much it. Actually, looks like a really easy part to hook up. One of the things though that I always wonder about is like, yeah, this is a cool part, this Intel Curie, and I would like to be able to take this part off of the board and design my own little custom board like I was showing you this. How would I do that? Let's see if we can find the part. Okay, so just found this website or this blog post here on TechCrunch. So we'll ship Q1 costing under $10. So we'll be able to buy this little part, I guess. Q1, I think Q1's over though. Is that 2016 Q1? So yeah, that's kind of cool. So here's just a image search of it. Oh, that's kind of neat. So this is showing like some kind of wearable there, and you've got the Curie. What else do we got here? Yeah, that's a nice shot right there. So, okay, so it looks like we'll actually be able to buy this part on its own and hook it up. But like I said, it's a BGA part. I can't find a data sheet for the Curie itself, so I don't really know the specs on it. I don't know what the pitch of the BGA pins are. I don't know how easy that's going to be to get a board manufactured with that part on it. So, couple things that concern me there. It's not as simple as buying, a strip of the TQFP 32 pins here, 32 pin part for the AVR, and then throwing that, put it into my reflow oven upstairs, and I've got boards made. The BGA part that's a little bit trickier than that. So, okay, so getting back to the schematic here, we've gone through the full Curie stuff there, and again, looks pretty simple. Looks like this is going to be an easy part to work with from a hardware standpoint anyway. Okay, so the last page here is the level shifting that hooks up to the headers. So this is all your digital pins. So this one here is for the analog, and then we've got 10 pin here for the digital, and then another 8 pin for the rest of the digital. And we've got level shifters going on here between the headers and the Curie. And what's this thing up here? Ooh, this. Okay, so we've got a little flash part on there. It's a It's a WinBond. Let's see what the spec is. 16 megabit, 104 megahertz, 8-pin SOIC. SOIC. So that's right there. And this is the flash for the part itself. So this must be what, I don't know if we have access to this from the Arduino IDE. I don't think that's for us. I think that's for the, I think that's where basically the firmware for the Curie, and maybe our sketch gets loaded in there and then it runs out of onboard RAM. I don't know. I have to look into that a little bit. But yeah, it looks like a pretty simple little flash memory chip there. So let me jump back to the schematic. And yeah, so it's a little SPI flash. We got the chip select, MISO, MOSI, write protect, and the clock. Cool. Okay, so then these are the level shifters, and I wanted to take a closer look at these. Let me pull up in the data. Okay, so these are multi-voltage level translators for open, drain, and push-pull application. Bidirectional. Interesting. I have not worked with this part before, so I'm interested to see how they work. Okay, so it looks like we've got, okay, yeah, this is good. So we've got A and B and an enable pin, and we have the reference voltage for the A side and the B side. So yeah, so the B side we are hooking to 5 volts, which would be the header side, through a 200K ohm resistor. And then the A side, which goes to the Curie, you would think just hooks up to 3.3, but it's actually 3.5 volts. I don't know why they did that. So we've got 5 volts and 3.3 volts, creating a voltage divider here to set us up with a 3.5 volt reference. I don't know what that's about. I'll have to dig into that a little bit. But these are bi-directional. So this is kind of like I did a video on level translators a while back with a single MOSFET. And I think that's basically what's going on here. They're bi-directional, but okay. So anyway, that's kind of a breakdown, first thoughts on the Arduino 101. Probably a much longer and much longer than it had to be kind of video there. Should have just kind of quickly skimmed through this thing and wrapped this video up. But anyway, that's kind of usually my, that's kind of how I work when I get a new board. I don't even plug it in. I just look at the hardware, try to get an understanding of what's going on, and then I plug it in and start playing around with it. But since this video is so long and it's getting late here, I think I'm going to wrap it up here, and we'll come back to this and start playing with some of the examples. We'll test out the Bluetooth stuff, the accelerometer, the gyro, and we'll do some testing too. I want to see what's going on with that analog input. I want to, and driving outputs from the Curie. Is it a solid driver or is it through a 200K? You know. So anyway, I'm probably missing something in there. I'm sure the smart Intel guys have figured all that stuff out. Here's the other thing too, by the way. I know I'm rambling like crazy here, but I just, this antenna here is kind of interesting. Look, it's got the hole, the other mounting hole right here. I mean, what if you did use a metal screw there? Wouldn't that screw up the antenna there? Just a thought there anyway. Okay, so that is the quick rundown on the Arduino 101 hardware, at least. Okay, so let me know in the comments below if you made it this far, because that would be a miracle. And thanks for watching.